All right then, good. All right, I'm pressing the go live button. And we are in theory live. Now, whenever I start the show, I always make the joke that we require some kind of external view to confirm our existence. But this time, I think our conversation will probably include topics that relate to this. So, Ken, how's it going?
Pretty good.
So for people who don't know who you are, who are you? What do you do?
I'm Ken Olum. I'm a research professor at the Tufts Institute of Cosmology. I study cosmic strings. I study inflation, philosophical issues connected with inflation, and a bunch of other things. Recently, I joined the NANOGrav collaboration where we study gravitational waves by timing pulsars.
Awesome. The philosophical implications of inflation. What's the philosophy of inflation?
Well, the problem isn't, it's not the philosophy of inflation, but that if you have eternal inflation, you end up with an infinitely large universe. And this gives us very deep philosophical problems that we don't know what to deal with, how to
What?
deal with.
Hit me with them. I would love to hear this. Maybe we can
So,
puzzle them out right now.
all right. So if the universe is infinitely large, then anything that can happen will happen.
Right.
And so we exist here. There will be other copies of us in vastly distant places, an infinite number of them,
Mm-hmm.
and all possible variations too. So there's another world, an infinite number of other worlds where you and I are having this exact same conversation, and also many more worlds where we're having very slightly different conversations, or we're having the same conversation except that little things are different because my name is Tom instead of Ken, whatever.
Right.
Um, there's many more ways for things to be different than there are for them to be the same.
And I've brought this up and actually done several videos on this idea. Just this idea that in any, say, cubic meter of space, you're going to have a finite amount of quantum information, and in an infinite universe, this finite information will be replicated an infinite number of times.
Yep, that's
And
exactly right.
and so whatever is possible that can exist will exist an infinite number of times, and every variation thereof.
Right. It's kind of a generalization of Murphy's law.
Right.
Anything can happen.
Everything, but I love that. That's awesome. Yeah, and the can go wrong will go wrong. And everything like, right can go right. Everything.
That's right.
Um, so then, I mean, it's bizarre and troubling, and obviously, when you think about an infinite universe, what is the philosophical problem of it?
Well, so what you would like to do is to say something about the probabilities for things. So, of course, there's all these copies of us, and some of them are going to have different things happen to them than others. So, some of us will finish our interviews. Some of us, the Earth will be hit by an asteroid before that happens. Most of the time, if I walk outside after this, everything will be fine, but sometimes I'm going to be hit by a truck. And I'd like to know how how common these things are. But there's a problem. I already snuck in something that didn't make too much sense. I said there are more versions of us that are slightly different than those that are the same. But what does it mean more? There are an infinite number of them. An infinite number of copies of me are going to be hit by a truck in an hour.
Mm-hmm.
An infinite number of copies of me are not. So what am I talking about
But
when
aren't there
I
different sizes of infinity?
there are different sizes of infinity, but these are not them.
Okay. All right.
So these are all countable infinities. You can make a one-to-one correspondence between the versions of me that will be hit by a truck and the versions of me that won't. You could think of this like the question of are there more, what fraction of the integers are even? Well, everybody would say a half, but on the other hand, for every integer, there's an even integer, which is twice that one. So, or I could count them in some funny way, right? I could say, let me count 1, 2, 4. Now I'll put in 3.
Mm-hmm.
Now 6 and 8. Look, there's twice as many even ones. It's not a well-defined question. So we need some philosophical plan that gets us out of this, that gets us away from this nonsense about it sounds like everything is equally likely because it's an infinite number of everything, back to some things are common and some things are rare.
Right. And I guess is the goal here to try to loop back around to consider our own existence, to say, is there some are we rare or are we common in having this conversation and not getting hit by trucks?
That's right. More importantly, from my point of view, what should we expect as astronomers if we look out into the universe? We see certain things, we'd like to know what we should expect to see next. We'd like to know whether the things that we see are expected or very unusual. And so you got to know what's likely. Of course, there's different theories of physics. You'd like to know which one is right based on your observations. In order to do that, you got to predict what the is going to happen based on some theory. So, for example, we built a big particle accelerator, the LHC, and we found many collisions in there which seem to be caused by the existence of a Higgs particle. So they said, well, okay, we've discovered the Higgs, but how do you know? Maybe there's no Higgs, and all those things just happen by chance.
Right.
Because anything that can happen is going to happen somewhere. So we just live in the funny corner of the universe where we got fooled.
Right. And I guess, I mean, we have this situation coming up again with the muon G-2 experiment. And I guess this is encapsulated by this idea of sigma. And so with the muon G-2, that's like 4.2 sigma, meaning it's like a 1 in, I forget what it is, like 10,000 chance that this isn't, or that it is random. And with Higgs, they're at like 6 sigma and beyond. And,
Right,
and that's when they think it's almost for sure not random, but it still could be random.
But we know that even if there's no extra physics, which is causing the G-2 anomaly, it could just be bad luck.
Mm-hmm.
And you say, well, but okay, but the bad luck would happen only 1 in 10,000 times, only 1 in 100,000 times, whatever. But how do you know that? It's happening. It's happening for certain. Mm-hmm. There are absolutely, if there's an infinite universe, there are civilizations which have bad luck, which are confused about particle physics because their experiments are telling them lies by chance. And so in order to say that it's not likely, so we know it's certain that some civilizations like that exist. You want to say it's not likely that our civilization is one of those, but we know there are an infinite number that are fooled, an infinite number that are not fooled, the same kind of infinity. So what do? You need what's called a measure, some way of assigning probabilities to these infinite sets. You need some kind of procedure. So for example, in a universe which is infinite and uniform, so it's just like, infinite space, it just goes on forever. There's a pretty simple plan that usually works. So let's just take a big sphere and let's count only the things that take place inside the big sphere. So, there's 10,000 of this inside the sphere. There's only one of that. So the thing which there's 10,000, it's much more likely. Now let's just keep making this sphere bigger and bigger and bigger and bigger. But always finite. Mm-hmm. You can make it as large as you want, and you'll still get, if something is more common in the normal sense, there'll be more copies of it.
Right.
So you can say probability is just frequency inside a gigantic sphere. And if the probabilities approach smooth limits as the sphere gets bigger, then everything is fine. So it's a simple idea to solve this problem in a particular case.
And so I guess like an analogy would be like we believe that thanks to the laws of gravity, planets are spherical, but it could also just be completely random chance that all of the elements, all of the matter in the entire observable universe has organized itself into these shapes, and it's a very rare fraction. But the larger this sphere goes, and the more of these spherical planets you find, the more your laws of physics explanation starts to approach one.
That's great.
Right.
If you just had one, you wouldn't know what it was. But if you have a huge number and they're dominated by one thing, and you can make this as large as you want. The problem is it doesn't work when you're trying to analyze different types of regions in the universe that are not comparable, or different universes in the multiverse, you might say. Um, so here's some part of the multiverse that's infinitely large, and the cosmological constant is what we have. Here's another part where the cosmological constant is twice what we have. Well, which of those is more likely? Well, now this plan doesn't work because they're all infinite universes. You can take where we are, you can make this sphere, you can make it as big as you want. You'll never get outside of our part of the multiverse. Mm-hmm. Nevertheless, there's other parts where the constants are different, maybe, we don't know. So we need some better plan for comparing it. And it is very difficult to come up with a good, philosophically motivated idea. What we'd like is for philosophy to tell us, like, this is the right thing to do. This is the thing that it makes sense to do. Instead, all we have is various ideas. And some of them give ridiculous answers. So we know those are wrong. Mm-hmm. Some of them give answers that seem at least sort of vaguely credible. But there is an argument that I made in a paper that really you can never do this right. There's always going to be some kind of paradoxical answer. And I don't know what to do about that.
Okay. Well, I mean, at this point, I think astronomers just go with this idea of homogeneity, that, and the Copernican principle that we don't exist in a special place in the universe, that everything is kind of the same no matter where you go, and it's the only way you can make any kind of productive headway. And I guess, yeah, there is a chance that you're operating in a very rare portion of the universe where the laws of physics exist in the way they do. But I mean, you mentioned the cosmological constant, but in fact, astronomers don't agree on the cosmological constant, and the error bars don't overlap. So, I mean, is that a hint that things might be a little weirder than we were expecting?
You're concerned about the Hubble
tension? The Hubble constant, yeah.
So, I don't think so. I mean, what it's a hint of, I don't know. It seems fairly likely that it's a hint of some kind of physics that we don't understand. And that's very important. There are probably 1,000 papers, each author explaining why their own idea is the right solution to this problem. Especially if they had the idea beforehand, and then this conflict came up and they said, look, I had this idea long ago, but there's hundreds of ideas. It's difficult to get any detailed information to try to vet all these ideas. So it's also possible that it's just mistakes in measurement.
Mm-hmm, of course.
And of course, it's possible that it's just some kind of weird chance effect, cosmic variance. Probably not. And if you asked me, the sense I have is that these people probably know what they're doing. I mean, I'm not the one who's making these measurements, but I would say it's likely that there is indeed some new physics. And what that new physics is, we really have no idea. People have tried to categorize the possibilities, and there isn't any great idea. This conflict doesn't point at a clear solution like, we've discovered, it has to be this. We don't know what it is, but there's something probably that's going on.
But I guess what I was wondering, that's just one example of a measurement at the vastest scales, which is starting to show discrepancies that might then give you a hint in how to resolve your philosophical conundrum, that you could, it gives you an approach. It would be nice,
but this is not, of course, at the vastest scales. It's at the biggest scales that we can observe. But right, those are very tiny compared to the whole universe, most likely. I mean, we don't know this either. Some people think, well, there was just enough inflation to make the size of the universe that we have. But most models of inflation are eternal, meaning they make an infinitely large universe. And they make an infinite number of every kind of universe. And we can't observe those at all. We won't be able to. So we can learn about the laws of physics by observing the universe we have. We can learn what the predictions of the laws of physics are for the part we cannot observe. And we could try to make sense of it all. But it is a difficult problem, which I think needs both advances in physics and advances in philosophy to figure out what we're doing and what we should be doing.
What do you think is the best approach that we could try to get a sense of the true size of the universe. Whether it, we know it's bigger than 96 billion light years, but we don't know how much bigger.
So the only thing we can do is to figure out what the process was that produced the universe that we have, and to see by analysis what size of universe that process would have produced. So we think it's inflation. Inflation solves many puzzles. It does a good job of explaining the universe that we have. We don't have anything which is really a smoking gun that says that it's inflation. There's one measurement, which is that the spectral tilt of the primordial perturbations is 0.96. It's clearly bounded away from 1. And so if it were near 1, you would say, well, forget inflation. Let me just think of the simplest thing I could possibly put in for a recipe for the universe. It's going to give 1. So we don't have that. We have something less than 1. Many models of inflation do give something less than 1. It tells us something about inflation. We would like to have very detailed information about that went into this 0.96. We'd like to get much more information of the same kind by studying the structures of the universe on all different scales very, very precisely. We would like to reconstruct the inflationary potential, the nature of the field that led to inflation, and then we could know what this did as the universe was growing very fast at the very beginning. This is a really tough measurement to do. And of course, you can also try to do it by coming up with theories, but the problem there is that there are too many of them. It's easy to speculate. Lots and lots of suggestions have been made. We need data to separate the suggestions, and the data is hard to get. It requires knowing how fast the universe was expanding at very, very early times. It involves knowing the size of the primordial perturbations that became the galaxies and the structures that we see with extremely high precision. So this is a tough thing, and we measure it as best we can. We'll have better measurements in the future, but it's going to be a long struggle to get the detail of measurement to try to really reconstruct what was going on in inflation. But that's the only way, except, some brilliant theoretical advance that somehow you say, well, there's one theory of everything. This is the right theory by just pure thought. I figured out the only theory it has to be. So people for a while thought that was string theory.
I've got a bunch of emails that have come in, probably even just today, that have proposed the theory of everything. So if you want, I could just pass them all along to you.
Yeah, I get many of these emails.
Right.
So people thought it was string theory, and there's a lot of reasons you might believe in string theory. It has some impressive accomplishments. But then they discovered this problem of the string landscape, in which there are vast numbers of compactifications of string theory, huge numbers of ways in which a universe, a model, a standard model, laws of physics like ours, could be embedded in string theory. And then string theory kind of lost its predictive value. So even if you're a string theorist and you're convinced that string theory is right, this still doesn't allow you to say, how did the universe inflate? Because there are too many ways. Mm-hmm. So that was disappointing to many people. It seems to be correct. And so now we're back where we were. We can only find out by precision measurements that are very hard to do.
What is the method that gets you at that 0.96? What is the actual observation that's made?
So this is done by measuring the details of the fluctuations in the cosmic microwave background. So you get this extremely beautiful curve of the microwave background fluctuation power as a function of angular scale, and it kind of goes like this. It has a bunch of little wiggles. I think they've seen about 11 of these little wiggles now, done by the Planck satellite, by balloon experiments, by things at the South Pole. Lots of different experiments have contributed together to give you this thing, and then you see what would this be with various models of how the universe developed, and you fit those models to the data that you see. And now you can tune model parameters and see whether they fit or don't. And that's how we learn what we have learned about this kind of thing.
And then what, you said that better observations, better techniques will be required. So what kinds of observations would you like to be able to make to be able to get more progress into trying to sense what happened right at the beginning of the universe?
So I think the thing which is likely to give us the best progress about this that we can foresee is probably 21 centimeter measurements. So 21 centimeters is the spin flip transition of hydrogen, and it measures something about the density of hydrogen clouds at early times in the universe. It is a little bit like the cosmic microwave background, except the cosmic microwave background is two-dimensional. It's like you're sitting at the center of the sphere of the sky, and what you see is the projection of all that stuff, the temperature of the cosmic microwave background at the time of recombination when the universe was 300,000 years old or whatever it was. So not exactly an instant in time, but basically a short period of time. You look back in the universe in any direction. So what you see is like you're at the inside of a sphere, and the sphere is colored in different colors based on the microwave background temperature, and all those maps are just that sphere unrolled into something flat so you can see it. 21 centimeter should tell us this same information in a three-dimensional way. So it will tell us the temperature of a certain kind of the universe in 3 dimensions at a sort of a snapshot at the past. So there's much more information there because it's 3-dimensional information rather than 2-dimensional information. So that will tell us a whole lot about what the universe was doing at certain times in the past from which this information can be gathered.
That's really interesting. I'd never sort of considered it from that perspective. With the cosmic microwave background, we're seeing every second that goes by, we're just seeing the birth pangs of a larger sphere of the universe around us. But with the 21 centimeter line, we're actually seeing these blobs of primordial hydrogen in their various shapes three-dimensionally.
That's right. It's sort of a snapshot of a certain time, 3-dimensional structure at a certain time. So there'll be a lot more bits there, a lot more data. I don't know. I'm not an expert on exactly what can be derived from that data.
What's the machine that's going to get us there? What's the instrument?
So there are a lot of these 21 centimeter observing systems. One is ALMA. One is CHIME in Canada. I don't know exactly the capabilities of these instruments. This is a big project to see through a lot of foreground noise and figure out how to gather this huge amount of information which is out there. The information in the cosmic microwave background we've mostly gathered. There's not that much. I mean, there's a set of experiments called CMBS4, which are going to be the next, like the successors to Planck, to observe the whole sky and look at the cosmic microwave background. But that's going to be about it for the information that we can get. And the problem is cosmic variance. Mm-hmm. What you're seeing is a chance process. And it's like you're trying to figure out whether a die is a fair die, whether it comes up 6 more often than the other numbers. Well, what you'd like to do is to roll this a large number of times and count the 6s. But we aren't rolling the die, we're only observing the rolls. And there's a finite number of observations that we can make. And so it's not like particle physics. Particle physics, you say, well, I did this and I discovered the top quark maybe, but only at 3 sigma. So let's do a lot more experiments. Here, when you do the observations, you've done them all. There's no new universes to observe. Right. So there isn't any way to roll the dice again. So that limits what we can do. And therefore, it's important to have a set of new observations, which are kind of like new rolls of the same dice that we can observe with different techniques.
Yeah, it's an interesting idea, this idea of cosmic variance that we're about to do the best possible observation of the cosmic microwave background that we can do under the laws of physics, no matter how good of a telescope we could make, we pretty much couldn't glean any more information. The problem is that the actual beginning of the universe is obscured by 300,000 plus years of opaque hot gas. What about going to gravitational waves, primordial gravitational waves? Would that get you some of the data that you need?
So you can certainly get a lot of things in primordial gravitational waves. If the gravitational waves left over from inflation can be observed, then we're going to learn a lot. And of course, we thought we had observed them. There was this big foofara with BICEP. Everybody got very excited, but it turned out to be wrong. The problem with that is that this depends very sensitively on the scale of inflation. So if the energy scale of inflation is high, these waves will be observed. But as the energy scale of inflation is somewhat lower, the gravitational waves are much weaker, and we don't know what it is. And it doesn't have to be that much lower before they're just so weak that there's no hope. So yes, it's a great thing if we're lucky. If we're lucky that the gravitational waves are there because the inflation scale was very high, that would be super useful. But otherwise, the information just is not observable.
Right. All right. So now, and stop me if I'm not understanding this correctly, but in your most recent paper, you talk about this idea of Boltzmann brains and there being an actual limit. And so allow me to stop me whenever I mess this up. But my understanding is that, of course, thanks to quantum mechanics, particles can reformulate themselves in various ways, depending on random probability. And so one of the weird philosophical issues is, what if you get to this point where atoms are reconfiguring themselves in a way that you're creating essentially conscious entities that are able to observe things, which gets kind of weird if you require some kind of observation to, say, collapse the wave function of some particle that you're literally getting.
The collapsing the wave function part.
Even just the existence of conscious entities appearing at random.
The problem isn't the general existence of conscious entities. The problem is the existence of copies of us. Mm-hmm. They could be anomalous copies of us in the sense that they aren't people at all. What they are is computers, some kind of little computers, very fast, that can somehow simulate our brains. So, I think that if you had a computer that could do a very, very accurate simulation of your brains, like all the neurons in your brain, and it would do exactly what you do. There would be a one-to-one correspondence between some data structures in this computer and neurons in your brain. And when the neuron in your brain would fire, the data structure would do something. That computer, and it would be, connected to some simulated body, so it could observe and it could act. That computer would be just like us. It would have the same thoughts that we would have, and it would have the same subjective experience that we would have. So just as we don't know if we're us in one Earth or us in some other Earth at a vast distance apart, we could also be this computer which is simulating us instead of us. Mm-hmm. So we don't know, because the computer's experiences would be the same as our experiences. Now, the problem is, what if either like an actual human body, which is exactly my body, or a computer, which is doing a great job of simulating me, appeared in outer space by itself as a quantum fluctuation? Then I would know if I am
whoops. I think we might have gotten a problem with his. Oh, there we go. There we go. Okay, sorry, we lost you for a second there. Okay, you're back. Oh,
sorry. I guess there's maybe some network problem.
Yeah, I think you're back. You're okay now.
Okay.
Yeah.
So Boltzmann brains, brains or humans or the whole Earth or a computer that simulates you, any of those things,
right,
appearing as a quantum fluctuation. And now you would say, this is like just unbelievably unlikely. Like, how unlikely is it to have just a bunch of empty space with a tiny amount of energy in it somehow fluctuate to make a human being? Well, of course, it's really tiny, so it would never happen. You wouldn't worry about it, except that there's an infinite amount of empty space. And so the concern is, if we just take our universe, we look in the very, very, very distant future, let's suppose the cosmological constant really is a cosmological constant. It won't change. Well, eventually, everything in the universe will cool off, and all the stars will go out, and all the protons will decay, and all the black holes will evaporate, and the universe will go on forever. Well, forever is a long time. And during that time, no matter how small the chances that a person might fluctuate, there will be a lot more people appearing by these fluctuations than actual human beings living on Earth today.
Yes.
And so by the general calculation that if there's a lot of one kind of you and a small number of another kind of you should expect to be in the large group, we should all expect to be Boltzmann brains.
Right. So, I mean, this is almost like the simulation argument, but made for Boltzmann brains.
That's right.
Yeah.
And of course, this is nonsense, because once you're a Boltzmann brain, then most likely all the memories that you have are false. Those things never really happened to you. Your brain just kind of fluctuated into a state of having those memories. And all the knowledge that you learned in the past about the laws of physics in the universe, the laws of physics with which we use to derive the existence of Boltzmann brains, are wrong. There's no reason to think that those are the real laws of physics. Those are just the laws of physics that by chance happen to fluctuate in existence in your brain. So this is called cognitive instability. If you start with a belief in the laws of physics as we have observed them, and as we've learned them through all our experience, you conclude that you're a Boltzmann brain who actually has no idea what the laws of physics are.
Right.
Okay, so this is a disaster. And it would be better to have theories which don't allow for domination by Boltzmann brains, don't lead to the conclusion that we are more likely to be Boltzmann brains.
Right. So that's interesting, because that's kind of even a more meta issue. So, my understanding of the philosophical problem of Boltzmann brains was more about the need to have an observer for some kind of quantum event. And so how can a quantum event create the observer? That's a paradox.
So I don't think observers are necessary for quantum events.
And I don't think that's necessarily the consensus, but sort of fairly early on, that was the idea, was just that, if, with, say, quantum entanglement, that you only get one outcome when you observe the particle going through, say, the double slit experiment or whatever. But what you're saying is that even our belief that the double slit experiment or something, Schrodinger's cat, requires an observer, could literally just be an understanding of the laws of physics implanted into the mind of a Boltzmann brain that has just appeared a nanosecond ago, and it's not real.
Right.
Yeah.
That's exactly right. So
that's awesome. I love it.
Yeah, there's no, it doesn't make any sense. So, you could consider, it's sort of vaguely related to the problem of solipsism. You could imagine, well, how do I know anything exists at all? I'm just a brain in a vat. No other people actually exist. The external world doesn't exist at all. And okay, like I can't talk you out of that position, but it's also a coherent position to think that the real world really does exist. And if you think that you're a brain in the vat and everything's random, then you're not going to have a very good life, because you can't make any decision. There's no basis to make any choice at all. It's a completely sterile view. So let's just put it aside, not because we're able to say that it's wrong due to some argument, but because it could be right, but you can go nowhere. Mm-hmm. The problem of Boltzmann brains is a little bit like this, but it's worse. Because if you start to say, I could be a Boltzmann brain or I could be a regular observer, then if I'm a Boltzmann brain, then probably I'm just going to evaporate in the next second, and there's no point doing anything. So, okay, fine. It's just like solipsism. Let me put that idea aside. Let me go back to the idea that I'm a regular observer. What are the consequences of being a regular observer? Uh, okay, that means that my observations are right. I get the laws of physics. I do the calculations based on the laws of physics. I figure out what they mean. Oh my God, they mean I'm a Boltzmann brain.
Right.
So it's not
Living in
now
a
just,
simulation. A Boltzmann brain living in a simulation. Yeah.
it's not just that I can't choose between being a brain in a vat versus not. The problem is when I choose, well, let me investigate the consequences of not being a Boltzmann brain. The consequence is that I am a Boltzmann brain.
Right.
So these theories of physics are nonsense. We can't we can't live with this kind of theory of physics. So, of course, what we hope is that that's not the right theory of physics.
Right.
Right? We hope that when we discover the right theory of physics, it won't be one that leads to Boltzmann brains.
And so you propose a mechanism that could be fighting in the opposite direction at a rate that is faster than Boltzmann brains appearing in the universe.
That's right. And this is not, this idea is not really a new idea. Our paper just points out some additional things that one has to take into account when one does this. So again, this depends on the choice of a measure in eternal inflation. We chose something called the scale factor measure. Why the scale factor measure is the right measure, I don't have any idea. It is at least a measure that works. It doesn't give crazy answers, pretty much. I mean, all measures are paradoxical, but this, at least many things work out okay. And there are a number of other ideas for measures that give something similar to the scale factor measure. In the scale factor measure, you could do a calculation of how to determine whether Boltzmann brains are dominant or whether ordinary observers are dominant. Which should you expect to be? And the answer is what you've got to do is to compare the Boltzmann brain formation rate with the vacuum decay rate, the possibility that your inflating vacuum can turn into anything else. So it could turn into a different kind of vacuum, and this is how all the different possibilities in the landscape get filled up. And the thing that we discuss is that it could also turn into a black hole. Mm-hmm. And when you count the rate of black hole production in this vacuum decay rate, and you compare with the rate of Boltzmann brain production, you discover that basically the chance of producing some little object in an inflating universe, in a slowly expanding, but inflating still, universe, like ours would be after all the matter had been diluted away. The chance just depends on the mass of the object. So the more massive the object is, the harder it is to make it. Mm-hmm. So there's some minimum mass for a Boltzmann brain. We don't know what it is. For an actual brain, it's like the mass of a brain. Mm-hmm. Or, like your brain isn't going to live for very long without your body. So maybe the mass of your body. Okay. So at least several kilograms. For a black hole, it's the smallest black hole, which is something around the Planck mass, about 20 micrograms. So since that mass is much less, the decay rate into black holes is much larger than the rate of making actual brains. So this solves the problem as long as the Boltzmann brain is, the minimum mass of Boltzmann brain is at least as massive as the Planck mass. And now you can ask the question, well, okay, for a brain, it's certainly true. What about the smallest computer that could ever simulate a brain and we don't know? Mm-hmm. I'm working with my student Param, with whom I did that. It was one of the authors with me on that paper on exactly this question about like, what is the minimum mass of a computer? But it's really all speculation. It is at least not an unreasonable speculation that you can't make a computer that can simulate a human brain and whose mass is less than 20 micrograms, because a human brain has an awful lot of data stored in it. And it's not clear how much you can miniaturize the computer. So if that's true, then our argument tells you that because the black hole production rate is higher than the Boltzmann brain production rate, that there's going to be more ordinary observers than Boltzmann brains, and we don't have to worry.
Why can't you have both? Why can't you have both black holes forming and Boltzmann brains forming? Just in
Well, you can. And then, of course, you should compare the number of black holes and the number of Boltzmann brains. But in this business, all the numbers are enormous. So if you look at the chance of the brain forming, it's e to the minus 10 to the some big number. And if you look at the chance of the black hole forming, it's e to the minus 10 to the some other big number, and that number is not as big. So, so these numbers, so the result is that the black holes are more likely. And these numbers are also huge, that any little change in anything makes the enormous number different from another enormous number by an incredibly huge effect. So it's like if I have, a billion, it's much larger than a million by a factor of 1,000. So it's 10 to the 3. If my number is a million digits long versus 2 million digits long, those numbers are enormously different. There's a million extra zeros.
Yeah.
And all the numbers that we have are like that, only much worse. And so some tiny thing. So if you ask, what's the chance of forming a black hole with 2 Planck masses versus a black hole of 1 Planck mass? Well, it's the question of the chance of forming one black hole, the 1 Planck mass black hole, and you have to square it to get the other thing. So this is already one chance in 10 to the 100, and the other one is one chance in 10 to the 200. They're vastly different. So that's why you never are going to end up with like, well, gee, I'm not sure, there's a lot of Boltzmann brains, a lot of black holes, which one is dominant? And for similar reasons, we don't have to worry about the difference between a Boltzmann brain and a Boltzmann brain, which is my brain or your brain. Of course, that's much less likely than any random brain. It could be anybody's brain. And in fact, mostly it's a brain which is not thinking any coherent thought at all. But those changes are small as compared to the chance of producing any kind of brain at all. And so once you're with these in this range of super enormous numbers, so that everything is just vastly unlikely, the sort of ordinary calculation of like, well, which thoughts are the brain thinking? Is it my thoughts or your thoughts? Those don't really make much difference.
So the idea of black holes, one of the, I guess, the handy side effects of generating black holes in this infinite universe is that a black hole with with this Planck scale mass is going to evaporate again and disappear. Right. And again, sort of my impression from your paper was that, you've got this pond and you're filling it up with, on the one hand, Boltzmann brains, and on the other hand, you're emptying it back out with evaporating black holes. And as long as the evaporating black holes is going faster than the Boltzmann brains appearing, then controversy is over.
That's right. Both of these things are happening at a ludicrously slow rate. So I talked about this big sphere that we might use in a spherical cutoff and taking the sphere to infinity. So in the scale factor cutoff, the cutoff is in how much expansion of the universe you allow before you reach the cutoff. So this amount of expansion, and again, what you do is you take a certain amount of expansion. So let me consider only the case where the universe has grown by a factor of 1 million. And then I'm going to not include any universes that have grown by more than that. And then I have a finite number of Boltzmann brains, a finite number of ordinary observers I compare. Then I take that limit of 1 million times expansion. And we give in the paper the size of number that you have to have. And it really is remarkably large. But the prescription says take this to infinity. Well, infinity is larger than any finite number, so that's okay.
Yeah.
So there is an incredibly slow process that once in a vast number of universes, there's one black hole of the Planck mass, and it lives for an infinitesimal fraction of a second and evaporates. And also, once in a huge number of universes, there's a Boltzmann brain. And both those things happen, but the number of universes it takes before you have a Boltzmann brain is enormously larger than the number before you have a black hole, even though both of them are huge. So almost nothing ever happens. Universes grows, huge numbers of universes are formed. Nothing ever happens. Very, very occasionally a black hole, even more occasionally a Boltzmann brain. The important thing is that the Boltzmann brain is less common. And so in this calculation, which I will not attempt to reproduce now, the tiny, tiny amount of black holes nevertheless overwhelms the even tinier amount of Boltzmann brains and reduces the amount of space in the vacuum in which the Boltzmann brains can form so that they end up overwhelmed by ordinary observers who exist mostly in not the universe that formed long, long, long ago because it's gone out, essentially. It's just going on and on with nothing in it hardly, but rather by a whole lot of other universes that have formed recently by this same process of eternal inflation, which is always forming every kind of universe in the multiverse. So these recently formed universes, which are still alive with stars and galaxies and people, those outweigh the Boltzmann brains that formed in the big empty universes, only because the volume in the big empty universes is depleted by these black holes.
Now, if you run, I mean, the Boltzmann brains are like, is like the bare minimum to get to a point of consciousness, but you can scale up the quantum randomness to the point that you literally get an entirely new universe. You could get a whole new Big Bang. Does this idea of the black holes, you know, if a Boltzmann brain is uncommon compared to the number of black holes, is an entirely new universe, but one that isn't a Boltzmann brain, that one is filled with actual observers, is that impacted as well? Are we cutting off the ability to have future universes at this point?
So the important thing here is inflation. So if you just imagined you and me and the Earth and the solar system, say, forming as a fluctuation, that would be harder than just like forming one person. And forming a whole galaxy would be harder yet. Forming, a billion galaxies would be harder yet. So those are not so interesting. But what's interesting here is that if I form a new inflating universe, this will then go on forever to form its own infinite numbers of galaxies. It will be like its own sub-multiverse with everything in it, with all possible inflating universes in it, with all possible people, with all possible, and Boltzmann brains too. Those are the things that matter here, and they matter because they're so effective. Like if you say, well, I'm going to form a person. Okay, I'm going to form two people, and all I get for that is two people instead of one. It's vastly less likely. I'm going to form a whole Earth populated with billions of people, even less likely, and all I get is a few billion. But when you make a new inflating universe, then you get an infinite number of everything.
Right.
So it really pays off.
And so I guess it's like a seed versus creating a tree from individual atoms.
Yes, I think that's a good way to say it.
Right. So we've got about 10 minutes left. I don't know if we have enough time for this, but sort of your main field of research, or had been for the longest time, is this idea of cosmic strings. What are they?
So if you think of a cosmic string, what could it possibly be? You're going to think the right thing. Something which is microphysically thin, astronomically long. So a tiny fraction of an inch across, and could be light years long, could stretch across the whole universe. Why might we have them? They could be the strings of string theory, stretched out very large due to inflationary models based on string theory. They could be topological defects in the vacuum. If you think about defects in a crystal could have a linear defect where the atoms don't line up. This is sort of a similar thing, only it's caused by symmetry breaking in the quantum field theories in the early universe. And so they could have formed when the universe was forming in the Big Bang. And then they could, once they formed, we know what would happen. We've done lots of big simulations. There would be a network of strings, sort of a funny, not really a net, but long strings that go on across the whole universe, and loops. A whole distribution of loops, small loops, big loops, medium-sized loops. there would be loops in our galaxy, there would be loops in intergalactic space. The loops would all be oscillating. Strings move around at the speed of light. So they'd be very, very massive objects moving very, very rapidly, and they would produce gravitational waves.
Mm.
And so what I've been doing recently is calculating the distribution of gravitational waves that come from strings. Because we are kind of on the edge of detecting the background of gravitational waves. Now, these would be, well, there are two kinds of things. There could be bursts of gravitational waves. So LIGO and Virgo have observed gravitational wave bursts that come from merging black holes and neutron stars. Cosmic strings could emit those, but it seems that the best hope for detection is not that, but rather the stochastic background of gravitational waves, the noise of all the loops in the entire universe, all oscillating in incoherent fashion, all emitting gravitational waves of their own, making just a sort of a noise that fills the whole universe. And NANOGrav has observed something which may or may not be a gravitational wave background of this kind.
I did see that, yeah, fairly recent.
So what we've observed is we can't say that this is a gravitational wave detection. It looks like some sort of a common noise process with a spectrum that we can put some fairly coarse limits on. That, and the best evidence we have is that this is a common spectrum which affects all of the pulsars that we time all together in the same way. So that could be the first sign of a gravitational wave background, such as would be produced by cosmic strings. It could also be something else, which is why it's not the claim of a detection. Nevertheless, since we don't have a good idea what the other thing would be that it would be instead, it's an indication that this may be a cosmic string gravitational wave background, or far more likely, a gravitational wave background which comes from pairs of black holes at the centers of galaxies. So we know a source. So we don't need to attribute it to a source that we don't know exists, like cosmic strings. Nobody knows if they're cosmic strings or not. We have some reasons to think they might exist, but that's completely unknown. We do know that black holes are at the centers of galaxies. We know that galaxies merge. We infer that the black holes in the merging galaxies must fall down to the center and orbit each other for a while and produce gravitational waves. So those are likely the gravitational waves that the NANOGrav is seeing if the NANOGrav signal is in fact caused by a gravitational wave background.
It's such a mind-bending idea that we're at the point with detecting gravitational waves that we're seeing this background gravitational wave radiation from all of the places where two supermassive black holes are orbiting around each other, or cosmic strings. We're not gonna discount that today. So back to this idea of what's the machine? What would get you a really nice answer to this question?
So we have more data from the pulsars that we've been timing, and we're processing that data now. In addition, there are other pulsar timing groups. There's a European pulsar timing array. There's one in Australia, which uses the Parkes radio telescope. There's an international pulsar timing collaboration that puts all these things together. So the first thing we need is more data. And we have some of it, so we need to process the data that we have. We need to gather more data. Part of it is just time. These gravitational waves that we're looking for have very long periods of the order of years. So the longer you wait, the longer you're paying attention to the same pulsar, the more information you can get out of it. We also need to find more pulsars. We need to time more of them. We need to time them more precisely. Eventually, we'll have this instrument called the Square Kilometer Array, which will contribute a lot of data to this field, but they haven't even started yet to build it.
I'm kind of imagining these like buoys on the ocean, and you're just measuring with lasers or whatever the distance to the buoys, and you're measuring them bobbing back and forth in all directions around you. but in this
Good
case,
analogy.
yeah, it's pulsars and it's gravitational waves that are washing across these pulsars, and so it's not about your ability to measure the gravitational waves directly as they are, say, with LIGO. It's about your ability to just more precisely time the bobbing of the pulsars as they spin. It's a phenomenal idea. Does it give you an ability to be more precise? Like could you start to use it as a telescope, or will it only just get you to there's a background there?
Well, you can't use it as a telescope and make pictures. But what we would really like to detect is a specific source. So there's various pairs of gravitationally bound black holes in the centers of galaxies, and one of those is the closest to us of all of them, and perhaps that one is loud enough in the gravitational wave sense that we could detect it. It would be a steady signal. And so one of the things that we do is to search for that. Is there one signal that it's like if you're in a crowded room and lots of people are talking and all you hear is noise, but maybe if one person is talking close to you, you could try to make out what that person is saying over all the noise. That's the kind of thing that we'd like to be able to do. And that's a possible detection that might be made in the future.
Or an island in my ocean of buoys that you're.
Well, no, it's more that one of the buoys is closer than the others.
Mm-hmm.
No, sorry. The buoys are where they are. It's that there's some sort of dominant wave pattern that's
Mm-hmm.
going over all these buoys, right? There was a storm 500 miles away. And now that storm is sending up big waves in a train of waves that are passing over all the buoys. What you'd like to do is to learn that that storm is there by seeing how the buoys get
Yeah.
closer and further apart.
Yeah. Perfect. Well, I was imagining waves reflecting off an island, but absolutely, that sort of makes the same thing. Ken, absolutely fascinating conversation. I really appreciate you sort of delving into both the philosophy and the cosmology of this. If people want to follow your work, see what you're working on, where should they go?
Um, well, I guess if they want to follow my papers, they should just read them on the Physics Preprint Archive. Um, I don't have any.
That's it. You communicate with the world through physics papers on archive and
Yeah, I think that's
perfect.
basically the best thing to do.
Yeah, no, I think that's like my favorite answer. You don't have a book, you just have a series of research papers that you've written. If someone wants to dig in, they can. Well, Ken, thank you so much for taking the time to chat with me today. I really appreciate it. Good luck. The NANOGrav is and I sort of wish, I feel like I kind of buried the lead there because I have been following NANOGrav and I'm really excited. We've covered that quite a bit on Universe Today. And so I think the most accessible chunk of this conversation is actually the work that's being done with NANOGrav. And so I think people should, if they're interested in this question, they should absolutely take a look at it. But again, thank you so much for taking the time to chat with us today.
You're welcome. It's been fun.
All right, take care.
Bye bye.